A very good afternoon, all of you. I hope I am audible. Participants, it is a request to all of you to mute yourself. Thank you. So now we are starting our session. A very good afternoon, everyone. I am Dr. Sushma Sharma, Assistant Professor from Department of Zoology, Deshbandhu College. Welcome you all to the virtual oral presentation session in ICHE Conference 2023. Today, before beginning of the session, I would like to introduce our chairperson of the session. So today, Dr. Aanchal Singhal is the chairperson for the oral presentation. It is my privilege to introduce ma'am, Dr. Aanchal Singhal. She is assistant professor in Department of Chemistry, School of Chemical Science, St. Joseph University. Ma'am has done her undergraduation and master's and PhD degree from University of Delhi. She is recipient of CSIR JRF Fellowship and Purushkar Award at St. Joseph University. Her area of research interest is green chemistry, heterocyclic chemistry, and biological chemistry. She has guided many research project students and PhD students. Ma'am has published so many research articles in reputed national and international journals. Now, I would invite Dr. Aanchal Singhal, ma'am, to take lead and start the session. Over to you, ma'am.
Thank you, Dr. Sushma, for your kind introduction. Yeah, we can start the session now. Thank you very much. I'm highly privileged and thank you very much for ICHE and the convener, Dr. Pratibha Kumari, for inviting me for such a great event. And I'm privileged to attend. I can't attend it all offline because it's a bit far. Right now, I'm in the Bangalore. At least I can be a part of it in an online mode. Thank you very much. Thank you again.
So for the presentation, our first participant is Meryl Shelley. Yes, ma'am, please share your screen. Ma'am, unmute yourself. You're not audible. Yeah. Your voice is not coming. No, ma'am, you are not audible. Achal ma'am,
I can hear you, Sushma ma'am, but I can't hear Meryl Shelley.
maybe she has some network issue. Meryl, can you please join it again?
Hello. Hello,
Yeah, yeah, we can hear you.
Now we
Yes.
can hear you.
Okay, okay. I'm Meryl Shelley. Here I'm presenting the topic. Here my presentation is on the topic, a comparison of the mechanical and biodegradable analysis of high-density polyethylene chitosan composites plasticized with palm oil. So a composite is a combination of two or more materials, which when combined together create a unique material, which is having the property of the constant materials they are made up of. In my work, I have prepared a biocomposite with high-density polyethylene as the matrix and chitosan as the filler. And this system has been prepared for biomedical application with improved mechanical strength and biodegradable property. This is a schematic. This is a schematic representation of the experiment which I have done. Initially, I have melted high-density polyethylene at 160 degrees Celsius, and to the melted mix, I have added varying concentration of chitosan. The compatibility of HDP and chitosan was improved by using dichromate peroxide as free radical initiator and malleconhydride as the compatibilizer. And a set of HDP chitosan composites were prepared, and the system was optimized with the help of mechanical strength. And to the composite having high strength, I have added various concentration of palm oil, having 2.58% of palm oil and 58% of palm oil. And these are the two sets of composites which I have prepared. And I have taken for the mechanical strength analysis. The mechanical strength has been studied by using the tensile strength measurements. And it was observed that with the addition of chitosan, the tensile strength of the composites were increasing, which is indicating the better interaction between the chitosan as well as the high density polyethylene. When palm oil was more comparable with that of experimental value, and the errors were within the limited range. And this is the total deformation and equivalent stress analysis of the samples. The same images of the tensile fracture surface was also taken. Here we can see that at zero concentration of chitosan, a wave-like morphology was obtained for the system. This indicates the ductile nature of the composite. When varying concentration of chitosan was added, this morphology was disrupted. At higher concentration of chitosan, the agglomeration has started to take place. And when palm oil was added to the system, the wavy nature was regained, which shows that the system has again attained the ductile nature. And the water sorption as well as the soil burial analysis of the prepared systems were also done. It was observed that when after 30 days of studies, the composites having high chitosan content started has shown high water sorption properties. And also, the soil mineral analysis showed that with the increase in the concentration of chitosan, the composites have undergone high degradation. And also, when palm oil was added to the system, the degradation rate was high. The mechanical strength analysis of the soil buried samples was also studied, and this was studied for 30 days, and it was observed that at the initial phase of degradation tends to attack the amorphous regions of the system. And for HC2 system, which is having 58% of chitosan, the system has almost has retained its tensile strength even after 1 month of degradation. And the water contact angle studies also shows that HC2 system has better filler matrix interaction and has decreased the soil and has decreased the degradation rate. So I am concluding that here I have prepared a biocomposite with nitrogen in many unhydrated compatibilized HPP system and its mechanical strength was analyzed. The theoretical studies was done by using ANSYS analysis and it has shown an accuracy of 85%. The closeness of composite to isotopic nature was also predicted with the help of finite elemental analysis. The palm oil has increased the segmental mobility of the system. With the increase in the concentration of palm oil, the segments could easily move so that the better interaction between the filler and the matrix was observed. And also it has led to the formation of a highly porous composite, leading to high water absorption and better biodegradability. The crystalline regions of the systems were maintained during the initial stage of degradation, and high mechanical strength was maintained by the composite even after degradation period of 35 days. So I would like to thank KICST for supporting this work and COSTAT as well as NIT Calicut for helping me to do the work. Thank you. Ma'am, can you hear me?
Any
Yes.
question? Yes, ma'am.
Oh, was I audible?
Yes, you are audible. I would expect participants to ask questions. Later on, I will ask. All right, Shelley, so nice presentation, I would say. So one thing I would like to ask, could you please go to the slide number 4?
Okay, ma'am. Okay.
So there, this thing is not clear that you are doing this mechanical strength analysis. And what is this error percentage? I can see that when you are doing it with HP1, I hope that HP1 sample is your, when you are infused it with the palm oil, correct? HP1 and
Yes, ma'am.
So here you show more error compared to that titration filler.
Ma'am, this I have compared the tensile strength values with the experiment values with the finite element analysis value. It shows that how much closeness is the values of my experiment data with the ANSYS value. When we are doing it finite elemental analysis, we are assuming that maximum interaction is taking place between the filler and the matrix. But here it is showing an error percentage of 17.2. It shows that the interaction between the filler and the matrix is not good, as well as the a fine homogeneous mixing has not taken place in the HP1 system. So that is the error percentage. It is showing the percentage is showing that better interaction is not occurring when I am adding 2.58% of palm oil to the HC5 system.
So you mean to say that samples with chitosan and not with that palm oil, they are better?
Yeah, the samples with chitosan are better than the samples with palm oil. But when I have also conducted the impact strength studies, which I have not mentioned here, in the impact strength studies, it is showing that palm oil plus samples are showing good strength. Means they have gaining better resistance when it is being subjected to an external force. But here I am showing with the tensile strength data only. In tensile strength data, when we are adding palm oil, this unsaturated centers of palm oil consumes the dicumal peroxide, now which I am adding the free radical initiator. It is consuming the unsaturated centers of palm oil. So the interaction, the palm oil is having little what kind of interaction between this filler and the matrix. So the interaction between chitosan and HTP is minimized in case when palm oil is added. So it is showing a high error percentage in ANSYS data, as well as in when I am comparing it with the theoretical values.
One more doubt. Could you please go to that conclusion slide, the last one?
Yes, sir.
So here it is mentioned that it contributes to the porous nature of the composite, leading to the high water absorption. So
Yes, ma'am.
how would palm oil help increase in the high water absorption?
My palm oil, when we're adding palm oil to the system, there's a high relaxation of the polymer chains. That is, the palm oil can improve the segmental mobility of the system. So I have worked on positron annihilation lifetime spectroscopy studies also. In the studies, it was shown that a large number of pores was formed in the system when palm oil was added. That is, the number of pores which is having very small sizes very high in palm oil added system. So the palm oil, it is mainly because of the segmental mobility caused by the palm oil in the system. So it is leading to the high water absorption and biodegradability.
Okay, which technique did you use to confirm that more porous nature of this compound?
I have used positron annihilation lifetime spectroscopy studies, PALS analysis.
All right, yeah, thank you.
Okay.
Now I would invite our next participant, Frankie.
Okay, thank you, ma'am. Thank you, ma'am.
Good evening, ma'am. Can you hear me?
Yes, ma'am.
Shall I share my PowerPoint?
Yes.
Is it visible, ma'am?
Yes, ma'am, it is visible.
Okay. I'm Dr. Francie, Assistant Professor of Chemistry from Holy Cross College, sharing my research work on comparative study on the alpha and HP alpha cyclodextrin inclusion complexes of stigmasterol. So stigmasterol belongs to a cholesterol family. It has vast application in the medicinal field. Even it can cure cancer diseases. So, but this stigmasterol is insoluble in water. So, to enhance its bioavailability, there are number of methods available. One of the method is inclusion with cyclodextrin complexes. So, I have taken this inclusion complexes so as to improve the solubility of this stigmasterol to be used as a bioavailability. So cyclodextrins are cyclic organic compounds obtained by enzymatic transformation of starch. There are different types of cyclodextrins are available, alpha, beta and gamma. I have taken alpha cyclodextrin because its aqueous solubility is higher than the other two and its cavity is minimum compared to the other. So this is alpha cyclodextrin, beta and gamma cyclodextrin. Here it's a stigmasterol, the compound I have taken for inclusion. So the inclusion complex will be within this cavity. That's my study. So I have prepared this inclusion complex by evaporation method. One I have taken a solid inclusion complexes with alpha CD and another I have taken solid inclusion complex with hydroxypropyl alpha CD, a derivative of alpha CD. I have also prepared liquid inclusion complexes with both the alpha CD. So here I have varied the pH medium and prepared the complexes. pH I have taken because I have want to use this complex in medicinal field so that we have two pH, blood pH as well as gastric pH. So I have taken the pH from 4, 6, 7 and 9 just to verify at which pH the complex is more stable. So these are the preparation method. So here, coming to the results, we have taken absorption studies varying the concentration of alpha CD. This is the UV plot obtained. So here the wave number is varied as the concentration varies and concentration of alpha CD varies. Stigmasterol concentration is kept constant. This is for HP alpha CD. So here the lambda max value is shifted from 260 to 258 nanometer on addition of hydroxypropyl alpha CD. This indicates the stigmasterol is entrapped in the cavity of HP alpha CD. So using Hildebrand equation, I have plotted a graph to find or to calculate binding constant of these both complexes. This is the equation used. And here is the plot by 1 by concentration of alpha CD was 1 by A minus A naught. There is a straight line obtained. From the slope, we calculate the binding constant value, and the binding constant is here 560 for HP alpha CD, and it is little lesser for alpha CD complex. So DSC studies I have taken for the solid inclusion complex sample. It is one of the method to confirm the inclusion complexes. So this is the DSC diagram for stigmasterol, and this is for alpha CD, and this is for HP alpha CD. This is for inclusion complexes of alpha CD with stigmasterol, and this is the DSC thermogram for HP alpha CD with stigmasterol. The peaks here, when the individual compound is there, peaks. And here, effect of pH, absorption studies on stigmasterol alpha CD inclusion complex. So here, as I mentioned, I have varied the pH value from 4, 6, 7, and 9, keeping the concentration of stigmasterol stable and varying the concentration of alpha CD. Here also, I have taken UV studies to confirm and to calculate the binding constant for these different pH values. So these are the inclusion complexes for alpha CD. This is at pH 4, this is at pH 6, and pH 7 and pH 9. So here it's indicating that the stigmasterol lambda max appears at 257 in the absence of alpha CD. But when alpha CD is added, there is a pathochromic shift. That is, lambda max is shifted from 257 to 296 nanometer. Similarly, for pH, it is shifted from 262. So all these spectral changes indicate there is an inclusion between stigmasterol as well as alpha CD. So this is for hydroxypropyl alpha CD and stigmasterol complexes at varying pH. This is for pH 4, and this graph is for pH 6, and this is for pH 7, and this is for pH 9. Here, the absorbance also vary, but for pH 4, there is no change in wavelength, but the absorbance varies. Here, there is a different peaks obtained when we vary the concentration of HP alpha CD. Similar results are obtained in these both complexes also. So here, an addition of HP alpha CD at different pH, the wavelength remains the same. At some cases, it varies with a different peak. So this is the graph plotted between 1 by concentration of alpha CD as well as 1 by A minus A naught. We get a straight line. From the straight line, we get calculate the slope, and calculated slope value, we calculate binding constant using Hildebrand equation. And here's another important information is when the slopes are found below 1, it is indicating the stoichiometry ratio between the alpha CD and stigmasterol is 1:1. So here also we have calculated the binding constant. And for stigmasterol alpha CD complexes, the binding constants values are obtained as 479, 463, 400 and 354 per nanometer for different pH value. So this is the pH plot obtained for different pH plot obtained for HP alpha CD complexes. Here also we get a straight line. From the straight line we calculate the slope value and calculate the binding constants. So the stability of the complex with HP alpha CD is higher. When we compare these binding constant, HP alpha CD is higher than alpha CD because due to the presence of the substituted hydroxyl propyl groups in HP alpha CD is the cause for this. So the substituent in HP alpha CD reduces the interaction with the aqueous region and enlarge the hydrophobic environment, enhancing the substrate binding via hydrophobic effect. Usually these inclusion complexes have a very minimum or very little force binding towards it. So here in my case, from other studies like NMR and computational studies, I have arrived the result as the stigmasterol, both end we have, one end only is getting into the wider rim of alpha CD, wider cavity of alpha CD. So the variation of cyclodextrin as well as pH also influence the complex formation, thereby enhancing the solubility of stigmasterol. So these are the binding constant. So when we compare this binding constant between alpha CD and HP alpha CD complexes, we have for all the binding constant value, HP alpha CD is higher compared to alpha CD. Similarly, when we compare the pH value, pH 4 gets higher binding value, that is at gastric pH. So the binding constant values of HP alpha CD and alpha CD inclusion complexes of stigmasterol increasing pH medium. It is because of the interaction of pi electrons of aliphatic carbon chain of stigmasterol with the CD. So increase in pH of the medium decreases the stability of the inclusion complexes formed, and hence the solubility of stigmasterol also will be decreased. Therefore, it is evident that most favorable pH for increasing the stability and solubility of stigmasterol is at pH 4 and less favorable at pH 9. So as a conclusion, stigmasterol forms the most stable complex with HP alpha CD than alpha CD, and it is at pH 4. pH 4 is the most favorable pH when compared to pH 6, 7, 9, and HP alpha CD is preferred in the formation of stable inclusion complexes of stigmasterol with alpha CD, with HP alpha CD than alpha CD. Thank you. These are the references. Hello, ma'am.
Thank you, Dr.
Yes.
Fancy. Nice presentation.
Yes, ma'am.
Yeah, I just have two questions.
Yes,
So
ma'am.
did you compare this HP alpha CD and CD binding with any other compound other than stigmasterol?
I have earlier done with the granatonin and with the resveratrol obtained from a fruit peel. They also give a good result, but I didn't go for further studies with those compounds. I took this stigmasterol because it's highly medicinal value, and I have isolated this from a local plant. That's why I wanted, because it is said this plant has high medicinal value. The plant is from Annona muricata, which is used for many diseases. So my interest was to enhance this bioavailability in pharmaceutical chemistry.
Yeah, I get it. So here, what I mean to ask this question, so according to the literature compounds, do you think your sigmasterol is working as a better binding with alpha CD compared to the other compounds reported in the literature?
That I can't be very sure, ma'am, because there are a number of inclusion complexes carried out in the literature. Apart from this, even other chemicals also they have taken. I went for biological studies, which show a better result, this inclusion complex.
All right. And one more, could you please go to that UV studies? Yes.
DSC,
No, UV studies.
this is it this or
There you
pH?
had shown that 4 UV spectra altogether.
Yes, ma'am. Is it this, ma'am?
Not really this one. The other slide was there where you were showing that effect of pH. Yes, this
Here?
one. Yes, yes. So here I want to ask, like when you see the UV spectra at pH 4, you can see that you have getting only one broad band, that peak maxima. While
Yes.
other pH 6, 7, and now you are getting that your broad peak is splitted into small peaks. What is the reason behind?
pH 4, hydroxyl propyl. This is, I mentioned hydroxyl propyl has a functional group, so which enhances the interaction with the stigmasterol in lower pH medium. Whereas the pH is higher, it has the interaction with it because the cyclodextrin cavity is hydrophobic and outside it is hydrophilic. So when pH is higher, that is a diluted condition, their interaction with the outside environment is more than the internal complex, internal pigment that we take.
So for example, here at pH 7, you are saying that the very first bottom line, there is very less peak maxima, and on adding up the stigmasterol, it is getting splitted into further peaks. So how do you infer from this data?
Stigmasterol also is a hydrophobic, which means like cholesterol, it's not soluble completely in water.
Correct.
Yes, ma'am.
Okay. All right. Yeah. Thank you.
Okay, now I invite our next participant, Dr. Mohinder Kumar. I think he has not joined. So I would invite our next participant, Dr. Saloni Sood.
Hello.
Yes, ma'am.
Hello, ma'am. Okay. May I share my presentation? Am I audible?
Yes,
Yes.
ma'am, you're audible.
So is my screen visible, ma'am?
No,
Not,
ma'am.
Ma'am, my screen is visible?
not yet.
Is it visible now?
I can't see. Others can confirm maybe.
No, ma'am, it is not visible.
Okay, just a second.
இல்ல பொடி வாங்கி கொடுத்துட்டு அங்க போய் சொல்லலாம்னு நினைச்சேன். இல்ல நான் சொல்லலாம்.
I can see my. Actually, I'm not using laptop right now, so I'm really sorry for this. To share my screen.
I think, ma'am, you rejoin. Okay, now, yes, ma'am, it's visible now.
Visible. Okay, thank you. I'm unable to do anything here. I'm sorry, it's about, I don't know, is it? Maybe. So is it visible now?
Yes,
Yes.
ma'am.
I'm really sorry for this. I'm Dr. Saloni Sood from Department of Chemistry, Government PG College, Nahan, District Sirmaur, Himachal Pradesh. And my topic for today's event, that is an international conference, is solventless synthesis and characterization of nanocrystalline cobalt iron top zinc oxide nanopowders. So as we all know, nanotechnology is important in each and every field, and it is an interdisciplinary subject which is finding a huge interest and novel users in improving the technologies for chemical, physical, biological, and biomedical applications. So some of the applications, as we know, of nanotechnology in the field of electronics, biotechnology, textile, defense, biomedical drug delivery, and many more. So in the field of nanotechnology, various nanoparticles have been synthesized, out of which metal oxide nanoparticle has been exploited as one of the most versatile materials. And when we talk about metal oxide nanoparticles, zinc oxide nanoparticles are material of choices because of their being chemically stable, easy to prepare, they are environmental friendly, non-toxic, biosafe, inexpensive, and biocompatible also. So zinc oxide nanostructures have been synthesized in one-dimensional, two-dimensional, three-dimensional structures, and they have been used in many areas, as we can see, from paints to medicines, sensors, food additives, semiconductors, cosmetics, and what not to say. So here we have prepared, here is a list of fabrication methods that has been used by a variety of researchers for the preparation or synthesis of zinc oxide nanoparticles, as well as doped and co-doped zinc oxide nanoparticles. So these methods, out of these methods, we have chosen the mechanochemical method because we have seen that the chemical which has been used and released during the chemical methods like sol gel and hydrothermal, they are providing, they are causing a risk to the human life as well as to the environment. Similarly, the physical methods involved in various methods which we use from previous researches, we have seen that they are costly. They use high temperature and pressure conditions for calcination and annealing, and they require large space area for setting up the machines. So from there, we took the motivation to prepare zinc oxide nanoparticles by eco-friendly and low-temperature mechanochemical method using two different synthetic strategies. One by oxalate method and another by digold method. In the oxalate method, oxalate precursor was annealed, and in digold method, we have annealed the diethylene glycoside precursor. So both these methods, both these strategies have been prepared by mechanochemical method, and they have used grinded the starting materials, the precursor which was obtained but annealed at the temperatures from 300 to 400, 450 degree temperature, and the zinc oxide nanoparticle has been prepared along with the side products which were washed or removed by simple method. So these are the synthetic strategies that we have used. In the first method, that is the oxalate method, we have used sodium oxalate, and for co-doping, we have used cobalt chloride, and iron. For iron, we have used iron oxalate, and zinc chloride is used as the starting material. So similarly, in the second method, we have used diethylene glycol instead of sodium oxalate. So in both these strategies, we have seen, these are the TGTTA data. We have seen that in case of oxalate method, the position of 18% corresponds to the molecules, and decomposition of 37.7, around 38%, is showing the loss of carbon monoxide and carbon dioxide. So we can see here in the first picture that at 493, around 493, we have obtained zinc oxide nanoparticles from oxalate. And similarly, in diethylene glycol method or dipole method, we can see there is one decomposition curve of 61.53. And this is showing that we have been obtaining zinc oxide at a temperature of 363.81. So then the structural characterization have been done using X-ray diffraction studies, and we can see that X-ray diffraction of zinc oxide, pure zinc oxide obtained from both these methods has very good results and strong and clear peak. Excuse me. This is the X-ray diffraction study of cobalt iron core dot sample, in which cobalt is 0.045 and iron is 0.005%. And absence of any extra peak in both these methods, whether it is oxalate and this is the dipole method, is suggestive of the fact that the samples were pure single phase and free from secondary phases. So there was no change in the Woodside structure of the zinc oxide. FTIR studies further confirmed the presence of high crystallinity and high purity of the zinc oxide nanoparticles. Then chem pictures, they have also suggesting the fine particles, agglomerated particles were obtained in case of oxalate method, and the particle size was between 15 to 30 nanometer range. So high quality hexagonal particles were obtained by these methods. Then by using the Mossbar spectra, we have simply used the Mossbar spectra to identify the presence of iron in our samples. So the Mossbar spectra also shows the that the doublet which has been then fitted using the software and cobalt and cobalt iron doped nanoparticles. And as we can see, a good hysteresis loop was obtained with a linear portion, which attribute to the ferromagnetic, open hysteresis loop attributed to the ferromagnetic, and the linear position that attributed to the paramagnetic nature in case of cobalt doped sample. So these are some of the studies which we have done, and with increase, we can see there is an increase in magnetization in case of co-doped samples. In case of cobalt iron doped zinc oxide nanoparticles, they have indicated that cobalt oxygen and iron exchange interaction in co-doped sample dominated, whereas iron oxygen iron and cobalt oxygen cobalt exchange interaction were dominated in iron doped as well as in cobalt doped samples. So in conclusion, we just wanted to compare two strategical method for the preparation of cobalt, iron, doped and co-doped zinc oxide nanoparticles. And we have seen by these two, by the characterization that the FTIR, XRD, and all these results, that the zinc oxide nanoparticles prepared after doping and co-doping are free from any impurity. There is no iron oxide or any other cobalt oxide impurities in the prepared nanoparticles. So we can prepare these zinc oxide based or cobalt or iron doped and co-doped zinc oxide nanoparticles by simple methods, eco-friendly methods. So this was the whole purpose of presenting this paper here, that there are a large number of methods and there are strategies which can be employed by various workers which are working around the globe for the preparation of zinc oxide nanoparticles, and we can obtain high yield at low cost using mechanochemical methods. So thank you very much for hearing me patiently. I'm really sorry for I hope thank you so much. If there's any question, I welcome all the participants for the question. Thank you.
I encourage all the participants to have a interactive session. Okay, nice presentation, Dr. Saloni. I really like it. And the one thing I just want to know that when you synthesize such compounds in which you need a high level of spectral characterization, is there any first point of contact through which you can recognize that your reaction is complete? Like, for example, grinding you are doing. So how long you need to do, or do you need to continue? Apart from that, PIR, is there any other technique through which you can identify? Because going for that XRD and going for that TGA, it is something like when you are sure that your sample is completed, your reaction is completed. I can't hear you.
Sorry, excuse me. For that, we have done FTIR at various stages. So it was just a grinding method and hand grinding we were using. And we were mixing the samples by weight, and then we were putting the samples for heating, because I was in Shimla, so the temperature was very low when we started. So we have to put the samples we were grinding for 15 minutes, and we were putting the samples inside the simple furnaces for 30 to 35 degree. Then we checked that the samples, they are not getting good results. We were not getting good results in FTIR. So we increased the temperature in the preliminary steps. So we were grinding at let's say 40 to 50 degree. We maintained that. We were grinding for 15 minutes, then we were heating the temperature for 5 to 10 minutes, then we were again grinding for half an hour. So this was the because there wasn't any method which we can tell that the nanoparticles are formed or not. So we used the FTIR method. So we have done IR studies. So a peak in the range of 400 to 600 is quite visible in our oxalate samples, precursor samples, when we started getting that peak. And so we were sure that we will get good result in XRD after getting good peaks in the FTIR studies first.
All right, thank you.
So our next participant is Dr. N. Mehala and M. Uma Maheshwari. Ma'am, let me share my screen.
Am I audible?
Yes,
Uma?
Yes, ma'am.
Good evening, everyone. I'm going to present a paper on analytical solutions of non-isothermal reaction diffusion model equations in a spherical catalyst by Akbari-Kanji method. This is one of the numerical method we make use of to solve nonlinear differential equations. And myself and my colleague Uma Maheswari will present the paper. First of all, let me tell you what is mathematical model. A model is nothing but a simplified version of a real life system or phenomena. Every real life system or phenomena can be modeled as a mathematical model, so that a complicated system can be demonstrated in a simplified version. That is this beauty of the mathematical model. It is a description of real life system using a mathematical language. So while the process of developing a mathematical model is known as mathematical modeling. So there are several methods to solve mathematical model. So let me show one of the model. The object of this paper is the land embedded boundary value problems are solved making use of the Akbari-Kanji method, which depicts the reaction diffusion equations in spherical catalysts as well as spherical biocatalysts. So the analytical results are obtained. The concentration of analytical solutions of concentration have been obtained for the chemical species as well as the effectiveness factors for dimensionless parameters. And then the obtained results are compared with the numerical solutions. These analytical solutions are compared with the numerical solutions by making use of the software MATLAB. Okay. Then now let's see the mathematical formulation of the problem. Biocatalyst equation. Here you see the differential equation, second order differential equation, which depicts the reaction diffusion equations of a chemical species in a spherical catalyst. Here the gamma represents the dimensionless activation energy, whereas the beta represents the dimensionless heat of reaction, and phi represents the Thiele modulus, which evaluates the surface of the spherical catalyst pellet. So here the equation is given with two boundary conditions. Then these are the dimensionless variables which are made use to make the equation into dimensionless form, which will enable the solving of the problem easily. So the given differential equation will be made into dimensionless by making use of the dimensionless parameter such as y equal to Ca by Cas. So the concentration will be converted into the simplest variable y equal to Ca by Cas. And then here also x. So we have employed so many parameters to make the equation into dimensionless variables. So, and then this is the effectiveness factor eta, which is also converted into a dimensionless form. Okay, after converting the equation into dimensionless form and making use of the boundary conditions, we will solve the differential equations by making use of the Akbari-Kanji method. This is one of the effective algebraic method to arrive the analytical solutions of various mathematical model, and it gives the effective and fastest, quickest results, and also accurate results. So this is the equation, and these are the boundary conditions. Here Akbari-Kanji method is employed through Taylor series method, because here one of the value y of 0 is obtained by Taylor series method, and then this is the analytical expression obtained by making use of the Akbari-Kanji method. Here the term y of 0 is obtained by making use of the Taylor series. So that's what it gives the effective solution. So that's what it is called the Akbari-Kanji method via Taylor series. Only the y of 0 will be obtained by making use of the Taylor series, and this is the solution of the concentration. Y of x is equal to y of 0 cos h inverse of 1 by y of 0 into x. So here you can see the analytical expression arrived after solving the differential equation by making use of the boundary conditions and applying the Akbari-Kanji method via Taylor series. Then here this is the analytical expression obtained for eta, that is effectiveness factor. These are the analytical expressions for eta as well as the concentration of the chemical species in spherical biocatalysts. And then the advantage of this method is the constant m in the method can immediately related to all the reaction diffusion parameters, so that the saturation parameter, so the geometric value of the problem via n. See, if you change the value of n as 0, 1, 2, you will get the planar, cylindrical and spherical diffusion respectively. The catalyst will become planar, cylindrical and spherical according to the value of n. If you change n as 0, you will get planar. If you n is replaced by 1, you will get the cylindrical catalyst, whereas if you replace n by 2, you will get the spherical diffusion. So accordingly. So this is the analytical expression got when n is replaced by 0. So this is the concentration for the planar catalyst, and this is the analytical expression for the cylindrical catalyst while n equal to replaced by 1. And this is for spherical. N is replaced by, in the analytical expression, we have to replace N by 0, 1, 2 to get the different analytical expressions for the different spherical biocatalysts, such as spherical, planar, and cylinder. And then see, after that, after finding these analytical expressions, we will these analytical results will be compared with the numerical results by making the use of the MATLAB program. That is called solution, which will be explained by my friend Dr. Uma Maheshwari. Uma, it's over to you.
Thank you, Meghala ma'am. And the concentrations obtained using Akbari-Ganji method is then compared by numerical simulations. The nonlinear differential equation with boundary conditions, as we discussed earlier, is numerically solved using MATLAB function called PDE-X4. Then the analytical solutions are compared with the obtained numerical results. The Taylor series is found to be the most effective method for obtaining the analytical expression for only the steady state substrate concentrations with the simulations. And let us discuss what is the observations after using the Akbari-Ganji method. So this method, along with the Taylor series method, gives a new, simple, and closed form of approximate analytical expressions for concentration for all the parameter values. In concentration, the parameter beta represents the dimensionless heat of the reaction, and as discussed earlier, phi is denoting the Taylor modulus. It is nothing but the mathematical expression that describes the relationship between diffusion and reaction rate. In general, this value is used to calculate the effectiveness factor. Now let us see the diagrammatic representation of the concentration of substrate or dimensionless distance x. When beta is modulated over 0.1 to 1 as well as 4, when the Taylor modulus is equal to 2, the first figure is obtained. And when we change the parameter beta as 1, then the second figure is obtained like this. And when we modulate the spherical, cylindrical, and slabs, that is the planar coordinates for phi equal to 2, then the concentration of the particles are illustrated here. So the first two figures clarifies that the concentration of the substrate for different values of heat of the heat reaction slab. And figure 1 specifically depicts that the concentration of the substrate for various heat reaction beta and Taylor modulus phi. The values for planar, cylindrical, and spherical particles are given separately. According to these figures, we found that the consequence of mass transfer and internal diffusion directs that the concentration of the substrate increases the heat of reaction, and the Taylor modulus decreases for all geometry, and the substrate concentration for spherical particles is higher than for slab and cylindrical particles. Also, in heterogeneous catalysis and solid fuel, the effectiveness factor is critical. In the porous catalytic pellets of solid fuel particles, the effectiveness factor, that is the Taylor modulus, is extensively used to account for the interaction between pore diffusion as well as the reactions on pore walls. Then the rate is calculated if the surface reactant concentration persisted throughout the interior of the particle. That is, there was no reactant concentration gradient within the particle, that is inside the particle. The rate of the particle's reaction can thus be suitably expressed as its rates under surface conditions multiplied by the effectiveness factor. So this is clearly explained in the figures. And these figures represents the effectiveness factor. The effect of Taylor modulus and the heat of the reaction number on effectiveness factor are described here. That is, the value of Taylor modulus when decreases, the effective factor increases quickly. That is given in the figure A and B here. When this process of diffusion rate is controlled, the smaller the effectiveness factor, the more extreme the intraparticle limitations. That is, these next figures illustrate that the substrate concentration for spherical particles is higher than for slab and cylindrical particles. They show the effectiveness factor for spherical, cylindrical, as well as the slab particles. By these figures, the slab particle has a higher effectiveness factor than the planar as well as cylindrical and spherical particles. And thus, it depicts the effectiveness factor for all the three particles, which was found that higher effectiveness factor than the spherical particle and the cylindrical one. So by this observations, we conclude that the solution of reaction diffusion problems inside biocatalyst particles using an approximate analytical method called Akbari-Ghanshi method. So this method is solved via Taylor series method, and it is used to obtain the analytical expression for the substrate concentration and the effectiveness factor for all the changes in the parameter values. The effect of the reaction, the heat parameter, and the Thiele modulus shape factor on concentration is also presented in this work. The other form is inferior to the slab shape in terms of mass diffusion transfer, resulting in a lower yield. The proposed approximation technique can be applied to several multi-component reactions in various biocatalysis geometries with sufficient precisions in the parameters. And these are the references we refer to complete this work. Thank you for this opportunity. Thank you all.
Nice presentation. So I just want to ask one thing, that what kind of catalyst did you use for your study, and what kind of substrate molecules? Basically, which reaction did you study?
Michaelis Menten kinetics, mostly membrane catalyst only will make use of. It may vary according to the chemical reaction. So whatever may be the catalyst, it can be modeled. So we can solve it by making use of different analytical methods. Our work is solving mathematical models by making use of several mathematical numerical methods. So the catalyst may vary from reaction to reaction. Mostly membrane catalyst. Here in this case, we have made use of a spherical biocatalyst.
Okay, thank you.
Thank you.
Ma'am, should we invite next participant?
Yes, please.
Okay, so I would invite Dr. Ritika Chauhan.
Good evening, ma'am.
Good evening.
Are you able to hear me?
Yes.
I should start sharing my screen. Are you able to see the screen, ma'am?
Yes, it's visible.
Okay. Shall I start, ma'am?
Yes, please.
A very good evening to one present here. I'm Dr. Ritika Chauhan, currently working as Assistant Professor in the Department of Applied Sciences, Bharati Vidyapeeth's College of Engineering, which is affiliated to ICHE University, Delhi. The title of my presentation is Persistent Organic Pollutants, which we name as POPs, the aphonic enemies of the environment. By the word aphonic, I mean they are real silent killers, and slowly and steadily they are a threat to the human health and the environment. So this is the outline of my presentation, which includes introduction, properties, detailed sources of emission, toxic effects, and how to combat the problem of POPs, the conclusion, and the references. So what are POPs? They are basically the toxic contaminants which are present in the environment that persist for a very long time. Even if they are removed, they will be present in small traces as they travel from one place to another, owing to the reason that they are highly resistant to the degradation, whether it's chemical, biological, or the light degradation. Then there are some properties that they are persistent in nature, and they have a long range transportability. Their ability to associate with aerosols, so they gravitate from the warmer regions to the colder regions like Alaska, and at low temperatures they do not degrade much, and they are semi-volatile in nature. They evaporate and they are absorbed on the atmospheric particles. So they are found in those places where they have not been originated. And also they are fat loving in nature, they are lipophilic. So they have this tendency to stockpile in the fat tissues of the animals, humans, and they bioaccumulate in the food chain. And they are tend to be more found in the meat and the dairy products rather than the cereals or the plant sources. So we as humans are at a greater risk of this POPs. Then I'm coming to the dirty dozen, which is also known as the legacy POPs. So this is a set of 12 POPs which have been identified by the UNEP Stockholm Convention, first held in 2001. So UNEP is the United Nations Environment Program, where the Stockholm Convention identified a list of 22 POPs which are of more risk, and out of that 12 notorious chemicals have been listed here, which have been classified on the basis of their structure, their origin, and their toxicity. So mainly are pesticides, and the main composition, they are containing chlorine in them.
Excuse me, ma'am.
Anji? Yes,
Ma'am,
ma'am.
your slides are not moving. We
Is it
can see
moving?
only the first slide.
Is it moving now, ma'am?
No, ma'am. Ma'am, please, please do the slideshow first.
Ma'am, it's in the slideshow only.
Ma'am, I think you have to share it again.
Okay, I'll start again. Ma'am, are you able to see now?
Ma'am, we can see the presentation, but it's the slides are not changing. You are showing the some commonly found POPs.
Yes, ma'am. Yes, ma'am.
Okay.
I'm on that slide only.
Yeah, okay.
I think there was some network glitch. So I was on this slide where I have listed a list of 12 POPs which have been identified by the Stockholm Convention. Out of those 12, I've listed only 6 here. So they are basically the organochlorine compounds, because CCl bond is quite stable to hydrolysis. So that is why they are tend to stay more in the environment. These are some of the sources of emission, starting from the agriculture sources, industrial effluents, combustion byproducts, and some research purposes. Mainly in agriculture, pesticides are used like DDT and iodine, and basically they are chlorine-containing compounds. They enter the food chain through plants and reach our humans, and they stockpile in the fatty tissues. So the older age people are at a greater risk because they have been exposed much to this the threat of POPs. Then the second source is industrial effluents, where the metallurgical industries and shredder plants and waste oil refineries are the major contributors. And main compound which is released from the industries are polychlorinated biphenyls. Combustion byproducts, by combustion, I mean the incineration process or the thermal decomposition process, which is carried out to reduce the amount of solid waste which is landing into the landfills. There, the organic compounds react with these chlorinated compounds which are there in the landfill to make polychlorinated dioxins and dibenzofurans. And also in research purposes, like the research stations which are lying in the polar regions like Antarctica and Mediterranean Sea, there the POPs have also been found because they have this ability to associate with aerosols, and they gravitate from warmer regions to the colder regions. Next is the toxic effect. Toxic effect is also found on humans and as well as the environment, because they are degrading the ecological balance of the entire system. They are found to be hormone disruptors. They tend to interfere with the learning abilities of the individuals. They are carcinogenic, mutagenic. They also induce hypertension, and they also shorten the periods of lactation in the nursing mothers. Coming to the toxic effects on the environment, they degrade the ecological balance. And I've already mentioned they tend to bioaccumulate in the food chain related to their fat-loving properties. They also lead to genetic changes because genetic changes in the flora and fauna. So once they are into the plant sources or the animal sources and we are consuming them, so they've already induced the changes, genetic changes in the agricultural produce, which will in turn will affect the physical processes which are going on in the organisms who are feeding on them. They also induce wildlife cancer and many other physical abnormalities. Now, the question comes how to combat this problem of POPs in the environment. So with all the industrialization, with all the developments in the agriculture, we have many more amount of POPs entered into the environment. So there are 3 main approaches. either we can put the control on the production and the usage. The second is either we can remove them. And the third and the most reliable or the most, you can say the relevant in today's age is the remediation methods. So I'll discuss briefly one by. So regarding the control of POPs, several initiatives by the United States and some by India have been taken where it prohibits the manufacture of different POPs. They have banned the release of dioxins and furans to the land, air, and water.
Excuse me, Dr.
Coming to
Ritika,
the,
I'm
yes,
not
ma'am.
very sure if the issue is with me, but I don't see your slides moving. It's still on the same slide.
I was about to mention this. We are not able to see these slides moving.
Ma'am, for me, the slides are moving. I'll share it again. I'm so sorry.
You
for
must have
this.
shared some other window. It seems like, no?
No,
And
ma'am.
also
No,
not
ma'am.
on the
I've shared the
slideshow board
same
also.
window. No, I've shared it again and it's in the slideshow now. Is it in the slideshow now?
No.
No, for me, it's in the slideshow
No.
only. Let me check again. Ma'am, which slide can you see?
Right now it's 11 for me, control of POPs.
Yes, ma'am, it's 11 only.
But from 6 to 11, now you have moved, so I can see 11. But since long it was on the 6, so we lose track what you are talking
Yes, ma'am, I understand, but I don't know where's the glitch. The internet is coming. Can you, without the presentation mode, can I present? Is it moving now?
Yes, now it is moving.
Okay, okay. So I'll present this without the presentation mode. So removal methods, there are several removal methods which are available for POPs, starting from the adsorption methods, electrochemical, and out of all these methods available, coagulation and flocculation have been studied widely because they are simple to operate and large amounts of organic pollutants can also be removed using these methods. So the process has two steps. The first step is using a coagulant which destabilizes the colloidal particles of POPs which are not able to settle. Usually the natural coagulants are used these days because they are biodegradable, they produce lesser amount of sludge, and they are more efficient at the low temperature, and followed by the process of flocculation where the larger flocks are formed, and then we can settle them, and then we can remove it from the solution we are treating. Are you able to see the slides are moving, right?
Yes.
The next method is remediation, where we can modify the existing POPs to some less hazardous compound rather than removing or controlling the release. So it involves basically the enzymes, modifying the enzymes at the enzymatic expression levels, modifying the activities and specificities of the enzymes. And remediation techniques basically involve the thermal, chemical, or biological, or the mixed version of these remediation techniques. So one of the examples I've mentioned here by the Ang and co-workers in 2005, which involved the phytoremediation. Phytoremediation means the remediation by using the plants. So remediation of polyaromatic hydrocarbons using the plant sources. And bioremediation, I mean the use of genetically modified microorganisms like rhizopar, pseudomonas, or arthobacter, which can basically react with these POPs and metabolize them and convert them into less hazardous compounds, which are of not much threat to the environment. And they have several advantages that they are able to withstand extreme conditions. They have this lock and key mechanism, so they have this effective catalytic mechanism, and economic viability is also there. So bioremediation methods are much more superior to the methods like adsorption or membrane methods or the electrochemical methods. Coming to the conclusion, I would say the POPs are increasing day by day. They are a great threat to all the biota, and they are creating much environmental problems. And owing to this ability to bioaccumulate in the fat tissues, and they are resistant to degradation. So there's an urgent need to research some more methods so that they can be removed or remediated from the environment, which is of great concern these days. So these are some of the references, and thank you. Hello.
Yeah, thank you, Dr. Ritika. It's good, but I'm not very sure if I missed some of the research work, but so what exactly you have done? Which method did you use for your work? Did you?
Ma'am, actually, it's a secondary research. It's basically a review article where I've compiled all the facts.
All right. Yeah. Thank you.
Okay.
So now I invite our next participant, Nikhil Quadra. Nikhil, are you there?
Good evening, ma'am. Yes, ma'am.
Excuse me. Hello, Dr. Sushma. I guess you have missed me. I'm Dr. Poonam Motsra. I'm
Sorry,
placed
ma'am.
here
Yeah,
before.
yes, I missed you. Sorry, Nikhil. So first we have to invite our participant, Dr. Poonam.
Sure, ma'am.
Ma'am, yes, over to you.
Yeah, shall I share my screen now?
Yes.
Are you able to see my screen?
Yes,
Am
ma'am.
I audible?
Yes, ma'am.
Yeah, okay. Yeah, good evening, everyone. My heartfelt gratitude to all the participants, our esteemed chairperson, Dr. Achal, and ICHE organizing team. Since our session is post-lunch and we have back-to-back session, so I appreciate your patience and attention just for a few more minutes. I'm honored to be a part of this esteemed international conference. And before you, I'm presenting an interesting topic, that is molecular iodine, a versatile catalyst for the synthesis of aryl imidazoles. Imidazoles, as you know, it has a diverse application in the pharmaceuticals. It has important application in the agrochemicals and material science. So thus making it a very, very important compound, and we must explore for the efficient synthesis, which is of paramount importance for us. Moving to the next slide. Allow me to introduce you to the highly substituted imidazoles. They are the class of compounds that hold immense significance in the field of chemistry. Imidazoles, you must be knowing that it is a 5-membered heterocyclic compounds with 2 nitrogen atoms. So imidazoles and their derivatives, they serve as a fundamental building blocks in medicinal chemistry. These are the compounds which have biological importance. These substituted imidazoles, they act as inhibitors of P38 MAP kinase. They have fungicidal and herbicidal properties. They act as plant growth regulators. They act as therapeutic agents. So thus highly substituted imidazoles, they play a significant role in the development of novel pharmaceutical compounds, which are less toxic, which are more potent. If we move beyond the medicinal chemistry or the pharmaceutical chemistry, they also have importance in the synthesis of advanced material. They can be used as ionic liquids or NHCs in heterocyclic carbenes, which give new dimension to the organometallics and to the green chemistry. Moving further, these imidazole derivatives, they have remarkable coordination properties, which make them a vital ligand. They form stable complexes, and these catalysts, these complexes, provide you an alternate or an efficient method for the synthesis of various compounds. So they are of industrial importance also. So thus in this context, we emphasize or we look for the alternative methods through which we can synthesize highly substituted imidazoles. So since I have mentioned that they have diverse application, they are of importance. So there are several methods reported in the literature for the synthesis of imidazoles. Most of them, I have listed few of them from the literature. The listed methods, they have several drawbacks. Like most of them, they require lengthy working hours. The required catalysts are expensive. They are hazardous. The yields are poor. Synthetic alternatives are many and varied, and they have restored to harsh reaction conditions. For example, we might have to look for the alternative methods which we should look for an alternative methods which are eco-friendly, where the catalysts are less hazardous, because the listed or the reported methods, they have poor yields, 40 to 90% yield of the product, even after 4 to 6 hours. So based on that, we explore the chemical properties of molecular iodine, which is inexpensive, which is non-toxic, readily available. So molecular iodine, it is relatively simple. Like if we compare it with the reported catalysts or reported reagents, phosphoric acid we use DMSO, we use copper complexes. So if we compare it with the reported methods, this is relatively simple. This has a low toxicity, which makes it an ideal candidate for the catalysis of imidazoles. So molecular iodine offers us this opportunity, and we tried the synthesis of imidazoles using molecular iodine. We tried synthesizing 2,4,5 triaryl imidazoles and 1,2,4,5 tetraaryl imidazoles from 1,2-diketones. In this broad program of developing array of compounds or a library of compounds, library of imidazoles, we explored the catalytic activity of iodine. We report a simple, rapid one-pot procedure where one-pot procedure for 2,4,5 tri-substituted imidazoles and 1,2,4,5 tetra substituted imidazoles. The reaction was carried out using benzyl 1,2-diketone, aniline, ammonium acetate, to a solution of benzaldehyde, and iodine we tried with the solvent ethanol at room temperature. Not just ethanol, we tried various solvents before actually reaching to ethanol. So the different solvents we tried were ethanol in toluene, ethanol in acetonitrile, in dichloromethane. But we used ethanol because it is relatively environmentally benign, and moreover, the aqueous workup is required in case of ethanol. Whereas in the other solvents which we tried, we need hazardous solvents for the extraction of the product. So we chose ethanol for the preparation of these highly substituted imidazoles. We standardized, after choosing the solvent, we standardized other reaction conditions. Further, we investigated or we carried out the catalytic evaluation of iodine. We used several mole percentage of iodine. We started with the 5, your lowest was the 5 mole percent. So we, starting from the 5 mole percent, we went up to 50 mole percent. In absence of ethanol, you can see from the table that we carried out the reaction for up to 4 hours, but the product was, traces of product was obtained. So, and just with 5 mole percent, we were able to get a good amount of product, which is around, not around, which is 99%. With the increase in the mole percent of iodine, we were able to reduce the timings or the duration of the reaction, but we zeroing or we thought of using 5 mole percent as the lowest concentration of iodine for the synthesis. After standardization of iodine, various temperatures were tried. So in order to examine the effect of temperature, concentration of iodine was kept constant at 5 mole percent, and the reaction was monitored at different temperature. You can see it from the other table on the right hand side. At elevated temperature, using 5 mole percent, better results in terms of yield and reaction time were obtained. So these are the two schemes, and we synthesized various imidazoles by varying the aldehyde, the aryl substituted aldehyde. When you look at table 3 and table 4, the substituents are of different nature. We used electron donating as well as electron withdrawing groups. So among the various products obtained, the result was significant for both the type of substituents. So we can say that it can be observed from table 3 and table 4 that the process tolerates both electron donating and electron withdrawing substituents on the aldehyde very well. The aryl group substituted with different positions of the aromatic ring has not shown much effect on the formation of the final product. This was the X-ray crystallographic data was done for a novel compound which we synthesized while preparing the library of imidazoles. The plausible mechanism which we predicted for the synthesis is that molecular iodine, it acts as a Lewis acid. So molecular iodine is capable of binding with the carbonyl group. So this increases the reactivity of the parent carbonyl group, the aldehyde, which we took, the aryl halide. As shown in this slide, we propose that the iodine facilitates the formation of diamine intermediate by activating the aldehyde group, which under mild acid catalysis of iodine condenses further with the 1,2-diketone, that is benzyl, followed by the dehydration, which eventually led us to isoimidazole, which rearranges via 1,5 sigma-tropic shift to the required imidazole, to the substituted imidazoles. After getting the good results with 1,2-diketone, we tried the synthesis using alpha hydroxyketones. So instead of 1,2-diketone, we replaced it with the alpha hydroxyketone. So there are several papers reported in the literature using 1,2-diketone, but there are very few papers in the literature using alpha hydroxyketone. So we took benzyl. Noting here that 1,2-diketones benzyl are usually prepared from benzoin. So in a way, if we are using alpha hydroxyketone, we have removed that step, that extra step which is required. So consequently, is a significant improvement in terms of green chemistry. Similar standardizations were done as we did it for 1,2-diketone. Various mole percentage of iodine were tried, and in this case, the best result was with 10 mole percent of iodine. So we chose 10 mole percent as the concentration of iodine, and again, various temperature levels were tried, and 75, we chose the highest. We did not go beyond 75, but our intention was to go for the synthesis which is not very harmful, where we do not require any hazardous condition. So there was improvement, no doubt, with the increase in temperature. But if you want, and if you have enough time, you can prepare it at room temperature also. But our team, we prepared it at 75 degrees Celsius. These are again a different library of compounds which we prepared using benzoin, alpha hydroxyketone. Again, the results with the electron donating and electron withdrawing groups were similar. There was not much difference. So after preparing the library of compounds, when we again tried to look for the literature data, we could not find any paper where you can synthesize imidazoles from benzoin without any use of oxidant. An oxidizing agent is required for that. So we tried to find out what significant improvement iodine has made. So we carried out several control reactions, alternative possibilities were checked, and we realized that iodine is promoting the aerial oxidation of benzoin to benzyl. You can see from the figure which I have shared that in absence of iodine, we did not obtain the product, that is benzyl. But in presence of iodine, the benzyl was obtained. When you carry out the similar reaction in the inert atmosphere, we flush nitrogen in inert atmosphere. Even in the presence of iodine, we were not, with only trace amount of benzyl was obtained. We did not obtain it after several hours. So that encouraged us that this has to be the aerial oxidation which was facilitated by the iodine. Looking at the literature data, we found out certain papers which show that iodine is capable of carrying out the conversion of benzoin to benzyl, but that too in stoichiometric amount. And in our synthesis, we were able to reduce the amount. We were using it in the catalytic amount. So that was the improvement which we did in the synthesis. So with this, I summarize my presentation. These are the various advantages which we encountered while synthesizing, while exploring the catalytic activities of molecular iodine. Firstly, as I mentioned, alpha hydroxyketone can be used as a starting material, and we can directly synthesize imidazoles. Ammonium acetate, which we were using for the synthesis. So when we look the reported or the literature reported methods, they were using ammonium acetate in many folds, like the very high amount of ammonium acetate was used. But in our synthesis, we reduced it to almost stoichiometric amount. We used ethanol in comparison to other hazardous solvents, which had easy workup. You simply had to put water and a product will come and will filter it. It is a multi-component synthesis where you can reduce the number of intermediates and thereby reducing the waste material, reducing the number of steps. And molecular iodine, as you all know, it is a mild reagent, easily available. It has several advantages. Thank you. Any question? I welcome any question if anybody has any query.
Nice presentation, Dr. Poonam.
Okay.
So I think we have already exceeded the time limit, so there will be very less time for the discussion. I just had few queries during the mechanism and one result slide where you had shown. Yes, no, after 10 more %, there was one data slide. Just before that. Before that. Just previous slide. Yes, over here. So here in the temperature control, you have shown that same, like aldehyde, you are using that same 4A, product is formed same 4A. You are having a temperature 45 degree. So you are getting 98% yield. Then I don't see any point in increasing the temperature because yield is same. You are not getting increase in the.
That I mentioned, ma'am. You can carry out the same reaction at room temperature.
But there is no effect on the of the temperature if you increase the temperature.
You were reducing the time, ma'am. That was the only purpose here.
No, I mean to say if you increase the temperature to a certain extent, then wouldn't it affect the reaction in a negative way?
Like if we increase the temperature, maybe we did not try it after 75 hours. 75 degrees Celsius.
Yeah, one more doubt is the mechanism.
Okay, which slide now?
That mechanism you have shown. Yes. Uh, Here, so could you please explain that when you are getting that hydroxyamine, then how if you are adding ammonia, then it will attack at this carbon center?
It will attack carbon center.
You are getting the product one, that diamino, how this amine reaction, this ammonia will be facilitated on this carbon. Is there any driving force for this reaction?
Okay. You are saying that from this single substitution of amine to di substitution.
And second thing, your iodine is reacting or forming a bond with this like that only. I mean, it is the and did you check about the reusability of iodine, or did you able to recover the iodine?
No, ma'am, we were not able to recover it. We while workup, we added solution of sodium thiosulfate, so we somehow consumed it, iodine.
All right, yeah. Thank you.
And anything from the mechanism, ma'am, what you were saying?
I think it's all right, yeah. Thank you.
So now I will invite Nikhil.
Yes. Is the screen visible?
Yes.
Okay, good evening, everyone. I'm Nikhil Kawatra. I'm a PhD research scholar in the Department of Biological Sciences and Engineering, Netaji Subhash University of Technology, New Delhi. The topic of my presentation is improving the bioactive composition of buckwheat using zinc oxide nanoparticles. So starting off with introduction, firstly, buckwheat is a highly nutritious pseudo-cereal crop that is widely consumed in European and Asian countries. The expected global market for buckwheat is about $1.4 billion in 2022 and is expected to grow to $2 billion by 2030. So the demand for buckwheat is continuously increasing because it is considered a functional food as it possesses various health promoting properties such as anti-cancerous, anti-diabetic, anti-tumor, and hepatoprotective. So these properties are associated with the content of secondary metabolites, which are present in buckwheat, such as phenolics, flavonoids, tannins, vitamins, and minerals. Among various phenolic acids and flavonoids, talking about rutin and quercetin, they exhibit antiviral properties, and they're also potential inhibitors of COVID-19. The content of these metabolites can be further increased by the process of elicitation. And there are various products of buckwheat, such as buckwheat microgreens and sprout, that are gaining tremendous attention. So by the process of elicitation, the content of these secondary metabolites can be further increased. So in this work, we have used zinc oxide nanoparticles for the process of elicitation. In the first step, the zinc oxide nanoparticles were prepared by thermomechanical method. Then the characterization of the nanoparticles was done using SEM, EDEX, STEM, and FTIR. After this, the nanoparticles were sprayed on microgreens and sprouts at different concentrations. After this, the extract of the microgreens and sprouts were prepared for the analysis. And in the analysis, we performed the phytochemical analysis. We analyzed various photosynthetic pigments and also the effect of various antioxidants that are present in microgreens and sprouts. After this, by using ultra-performance liquid chromatography, we also analyze the effect of nanoparticles on the content of rutin, quercetin, gallic acid, ferulic acid, and vanillic acid in both buckwheat microgreens and sprouts. After this, coming to results, this is the characterization results of the zinc oxide nanoparticles. So with the FESM results, we got to know that the zinc oxide nanoparticles had a tube-shaped morphology. With the SEM EDEX concentration that we evaluated and found, the zinc and oxygen concentration proved that the zinc oxide nanoparticles were formed. The HRTEM pattern confirms the growth of zinc oxide nanoparticles in the C-axis, and the grain size was obtained to be 14 nanometer. After this, the effect of zinc oxide nanoparticles on the phytochemical compounds. In the buckwheat microgreens, the application of zinc oxide nanoparticles at different concentrations of 50, 100, and 150, it significantly increased the content of various phenolics, flavonoids, flavonols, and tannins. The maximum content of these compounds was achieved at a concentration of 50 mg per liter in microgreens. Whereas talking about sprouts, the treatment of nanoparticles at a concentration of 10 and 50 mg per liter increased the content of phenolics, flavonoids, flavonols, and tannins. Comparing the two microgreens and sprouts, the buckwheat sprouts had a higher content of phenolics as compared to microgreens, whereas the microgreens contain more amount of flavonoids and flavonols in comparison to sprouts. Talking about the antioxidant activity, the effect of zinc oxide nanoparticles on the antioxidant activity, the DPPH radical scavenging activity increased at concentrations of 50, 100, and 150 mg per liter in microgreens. The FRAP antioxidant activity also increased with 10, 50, 100, and 150 mg per liter concentration. In buckwheat microgreens, the nitrite scavenging activity was increased by 200 mg per liter concentration. While talking about sprouts, the DPPH concentration, the DPP radical scavenging activity and FRAP antioxidant activity, it was increased at concentrations of 10 and 50 mg per liter. Buckwheat sprouts, basically they exhibited higher content of DPPH, FRAP, and nitrate scavenging activity as compared to microgreens. After this, the effect of zinc oxide nanoparticles on the sugar content and protein content. Talking about microgreens first, the total sugar content considerably increased at concentrations of 50, 100, and 150 mg per liter, with the highest content of 16.74 mg per gram that was attained at a concentration of 50 mg per liter. In buckwheat sprouts, the sugar content increased significantly when it was treated with 10 and 50 mg per liter concentrations. The total protein content in buckwheat microgreens treated in nanoparticles was either equal or less when compared to control microgreens, whereas in buckwheat sprouts, the protein content increased with the zinc oxide nanoparticles at all of the concentrations. After this, the effect of zinc oxide nanoparticles on the photosynthetic pigments, the total chlorophyll content increased at all concentrations in buckwheat microgreens when treated with zinc oxide nanoparticles, with a maximum level of 0.287 mg per gram that was achieved at 50 mg per liter concentration of nanoparticles. In buckwheat sprouts, also the content increased at all concentrations when treated with nanoparticles. The chlorophyll content was found to be almost twofold in buckwheat microgreens in comparison to sprouts. The total carotenoids increased in buckwheat microgreens when treated with nanoparticles at 10, 50, and 100 mg per liter concentration. The maximum carotenoids were obtained in both microgreens and sprouts at 10 mg per liter concentration. So this 10 mg per liter concentration was optimum for the increase in the content of carotenoids in both microgreens and sprouts. After this, the ultra-performance liquid chromatography was performed for the analysis of rutin, quercetin, ferulic acid, gallic acid, and vanillic acid. So talking about microgreens first, the amount of rutin, quercetin, ferulic acid, and vanillic acid, it significantly increased with the treatment of nanoparticles at 100 and 150 mg per liter. Talking about sprouts, the content of rutin, ferulic acid, and vanillic acid significantly increased with the treatment of 10 mg per liter nanoparticle concentrations. Coming to conclusion, the maximum content of the most of the phytochemicals, sugar content, and antioxidant activity in buckwheat microgreens and sprouts can be obtained when nanoparticles were sprayed at 50 mg per liter and 10 mg per liter. So for microgreens, the optimum concentration of nanoparticles was 50 mg per liter, whereas for sprouts, it was 10 mg per liter concentration. A higher concentration of most of the bioactive compounds was obtained in buckwheat sprouts in comparison to microgreens. So therefore, we can say that the consumption of sprouts could confer greater nutritional benefits as compared to microgreens. With our research, the new avenues have opened for investigating the fate of zinc oxide nanoparticles in plant-based foods, as they may exhibit extraordinary biochemical and therapeutic properties. Thank you.
Nice presentation, Nikhil.
Thank you, ma'am.
So I think I lost track if you have mentioned, so I can see that all the data and it's very fascinating, but I did not, I mean, which technique are you using to get this data? If I think I have lost the track.
First of all, the nanoparticle they were sprayed on the microgreens and sprouts, so the extract was prepared for both microgreens and sprouts. So after this, the assays that were used for total phenolic content, the calorimetric assays especially. So we used the calorimetric assays for determining the content of phenolics, flavonoids, flavonols, tannins. And other than that, for determining the content of phenolic acids such as rutin, quercetin, and gallic acid, we have used ultra performance liquid chromatography.
All right, and very good. So, like we say that every good thing comes with a drawback. Did you see any negative effect or side effect of zinc oxide on spraying on the food particles?
Yes, ma'am. Actually, in a few, because there has to be an optimum concentration for the bioactive compounds to enhance. So, at a concentration of 200 mg per liter. So, we have used 10, 50, 100, 150, and 200. So, mostly at 250, the content of the bioactive compounds have started to increase. So, the optimum concentration is 10 and 50 that we can use for microgreens and sprouts. So, after a concentration which is higher, which can be toxic also, for microgreens and sprouts, the bioactive compounds have started to reduce at 200 mg per liter. So the optimum concentration is very important for application of nanoparticles on plant-based foods.
All right. What kind of side effects did you observe on increasing the concentration?
Now, on increasing the concentration, for example, I can show it to you that, for example, if you see that the concentration of such suppose flavonoids, they have also started to reduce. At a concentration of 10, the content has increased, talking about sprouts, the total flavonoid content, whereas after that, the content has also reduced. So this is also one of the side effects of zinc oxide nanoparticles. So only at optimum concentration that we have evaluated, we should be using zinc oxide nanoparticles for enhancing the content of bioactive compounds.
Very good. Thank you.
Thank you. Now I'll stop sharing the screen.
Yes. So now our next participant is Ms. Divya Sinha.
Yes, ma'am. Good evening, ma'am.
Good evening.
Are you hearing, ma'am? Hello, ma'am.
Yes, we can hear you. We can hear you.
Okay, ma'am. Are you able to see my slides?
Yes.
So let me start. Let me start, ma'am.
Yes, please.
So welcome everyone. I am Divya Sinha, a PhD scholar, a student, is going to represent a presentation on the topic of characterization of green synthesized nanoparticles through UV spectroscopy. Under this topic, we will explore about what is nanoparticles, why it is becoming more important for us, what is green synthesized nanoparticles, but why we need to characterize nanoparticles, and the principle of UV spectroscopy and its application in studying the characterizing these nanoparticles. So as we hear in this slide, we will present that engineered nanoparticles is one of the fastest growing technology of the present world. We often hear about nanoparticle based materials like nanosensors, nanocarbon tube, nanobiofertilizer in our daily news. Now the question arises is, what does this nano means? The nano, why does this nano means, and why it is becoming more popular and crucial for us? The simple answer is that the nano is simply nano is simply refers to a nano scale, which is a scale of objects and phenomena that are measured in nanometers. A nanometer is 1 billionth of a meter, so it is a very small unit of measurement. So nanoparticles can be defined as the particles whose sizes ranges between 1 to 100 nanometer. And it being such a smaller in size, nanoparticles exhibit such an effective and unique physical and chemical properties than bulk materials of the same substance. These properties include that high antibacterial properties, high magnetic properties, and high optical properties, the nanoparticles that exhibit. So due to such unique properties, nanoparticles applications can be seen in various fields of our life, in medicine, in electronics, in energy generation, and other material sciences. So next, I will discuss about the synthesis of nanoparticles. As you able to see from my slide, that the synthesis of nanoparticles involves two approaches. The first is top-down approach, and the second is bottom-up approach. The top-down approach involves the physical process of synthesis, in which the bulk substances is simply break down into a nanoscale size particles by using physical processes like mechanical or lithographic methods, methods. But the use of this physical process involved is highly most costly. Most costly. The second approach is the bottom-up approach, approach which involves the two processes, the chemical methods and methods of synthesis of nanoparticles and green synthesis process. The chemical process involves include the reduction, precipitation, hydrothermal, sol-gel emulsion, and micro-emulsion process. These processes are faster at producing bulk materials, but they are also require expensive and hazardous substances which are detrimental to the environment as well as health. The third is the green synthesis process. The biological process is the green synthesis process uses biological agents and natural extracts for the synthesis of nanoparticles which are more environment friendly. So the green synthesis the aims of green synthesis nanoparticle is to reduce environmental and health impact and associated with the conventional nanoparticle synthesis methods. The types of natural extract that the green synthesis process includes are plant extracts like leaves, roots, fruits, seeds, etc. Microorganisms like bacteria, fungi, algae, and other organic waste. These processes are safer for environment and human as it requires no toxic chemicals for synthesis. Bioactive compounds like terpenoids, flavonoids, etc. found in the biological compound itself act as a reducing and capping agents and a stabilizing agent. So it is less cost effective, less energy, and more eco-friendly, and produce large amounts of nanoparticles due to easy availability of resources. Another important of green synthesis of nanoparticles is that it follows the 12 principles of green chemistry that was given by Paul Anastas and John C. Warner. After synthesis, characterization of nanoparticles becomes more important for its better application. There are 4 requirements. Here I have represented the 4 importance of characterization of nanoparticles. The first is about the quality control. It ensures that the quality and consistency of nanoparticles, which is vital in fields like medicine and
Divya, you have crossed the time limit.
Yes, ma'am.
You have crossed the time limit. Please finish it quickly.
Okay, ma'am. The importance of characterization techniques are the quality control, understanding the properties of nanoparticles like size, shape, and aggregation state, etc. Because the nanoparticles size and properties were. Sorry, ma'am. So the third is the tailoring. The most importance of factorization of nanoparticles is for tailoring a specific applications. For as we know, the nanoparticles varies. The properties of various properties of nanoparticle varies with their size and shape. So characterizing nanoparticles is more important to characterize the specific properties of nanoparticles. Now we will discuss about the importance of UV visible spectroscopy in characterization. As we know, there are many other techniques used for characterizing nanoparticles like SEM, PEM, XRD, etc. But the importance of UV spectroscopy in characterization is that it is easy to operate, short time measurement, requires low concentration, and more economical than other techniques. The principle of UV spectroscopy. The UV spectroscopy deals with the following principle. First, the interaction between the UV visible light and the particles, electronic transition. UV spectroscopy primarily deals with the transition of electrons between different energy levels within the electronic structure of molecules. Molecules have energy levels associated with their electrons, and these levels are quantized. The third principle of absorption of UV spectroscopy is the absorption of UV light. When a molecule absorbs UV light, it promotes one or more electrons from their ground state to an excited state. This transition requires energy equal to the energy difference between the two electronic states. The third is Beer-Lambert law. UV spectral principle is work on Beer-Lambert law to determine the concentration of nanoparticles. The third is UV spectroscopy, and the UV spectrophotometer is used to analyze is used in UV spectroscopy to determine the characterization of nanoparticles, which give a spectrum which is known as the UV spectrum. Here is the instrumentation of UV spectrophotometer, which consists of a light source, a monochromator, a beam splitter, and a detector and a recorder. After using a UV spectrophotometer, we got a graph which is a absorption versus wavelength graph. This graph, the graph that here we are representing lambda max, give the color of nanoparticles, or we may say that the functional group of nanoparticles.
Excuse me, Divya, please finish it quickly because you have crossed the time limit.
Okay, ma'am. Information from UV spectroscopy. The following information we get from UV spectroscopy: size, concentration, shape, aggregation state, surface composition, and distribution. This is the case study that I have read about the size distribution of nanoparticles, concentration of nanoparticles that varies according to the absorption and absorption, size distribution of nanoparticles, shape of nanoparticles that varies according to the absorption of light, surface composition. Thank you. Thank you, ma'am.
Ma'am, would you like to ask questions?
Can you tell me which method you used for the preparation of nanoparticles?
Ma'am, green synthesis method, that is plant mediated synthesis of nanoparticles.
Okay. Okay. So, and by which method you have calculated? What is the size of your nanoparticles?
Ma'am, now I am a PhD scholar. I am just doing a literature survey. That the data that I have, or graph that I have put it here is from the previous work that many scholars has done, scientists has done.
Okay, that means you are going to do in your future work, right?
Yes, ma'am.
Okay. what is the what application you are just thinking that nanoparticles are doing this thing or that thing? So what applications you are thinking of from your expecting from your nanoparticles?
Ma'am, I'm not. I have not decided it, but
because this is the basic question. Whenever we do the research, it
but
becomes.
if
I mean,
nanoparticles has wide application, we may go through anywhere either in environmental management or any medicinal industry. That the for, but I have not decided it. Not.
okay. Okay. Thank you so much.
Thank you.
So our next participant is Mr. Amos. I think are you there?
Yes, ma'am. Am I audible?
Yes, yes.
Okay. Can I share my screen, ma'am?
Yes.
Okay, ma'am. Can you see my screen, ma'am?
No. Yes.
Can you see it?
Yes, yes.
Okay, thank you, ma'am. Okay, thank you. My name is Amos Luanda. I'm research scholar from the Department of Chemistry, Postgraduate Studies and Research in Chemistry, Mangalore University, Karnataka. So today I'm going to share with you one of my research work titled Evaluation of Drug Release Efficiency of a pH-responsive dextran-based silver nanocomposite hydrogel using curcumin as model drug. I don't know, my slide can't move. Hello, ma'am. Am I audible?
Yes, you're audible.
Yeah, but my slide can't move. I put this presentation mode. Don't know, let me share it again. Sorry. I don't know, still it can't move and still in presentation mode. And I try to escape it can't. Can you see it, ma'am?
Yes.
Okay, I put again presentation mode. Yeah. So my name is Amos Luanda. I'm a research scholar from the Department of Postgraduate Studies and Research in Chemistry, Mangalore University. So I'm going to share with you one of my research work titled Evaluation of Drug Release Efficiency of a pH-responsive dextran silver nanocomposite hydrogel using curcumin as a model drug. So introduction, effective cancer therapy is one of the global critical medical challenges due to poor solubility of many anti-cancer drugs, quick metabolism, side effects, limited specificity, and so on. So what to do to eliminate these challenges? Nanotechnology continues to be a driving force in the development of innovative and personalized cancer treatment. And this approach offers a promising avenue to overcome the challenges of cancer therapy by revolutionizing drug delivery systems. And these delivery systems enable sustainable drug release, combination therapies, reduce side effects, and targeted drug release. Curcumin is a highly lipophilic naturally occurring anti-cancer drug. It has phenolic and diketone moieties and is commonly used for treatment of various types of cancer, including lung, colon, kidney, breast, stomach, and so on. However, its bioavailability is highly limited by its poor solubility in aqueous environment, hence affecting its therapeutic efficacy. So in this study, we developed the dextran-based silver nanocomposite hydrogel as a delivery system for sustainable release of curcumin. Using dextran, which is a water-soluble polysaccharide originated from microbial origin, consisting a glucose unit, using also incorporated with 4-acrylomorpholine, which is an acrylamide derivative and a water-soluble monomer with good biocompatibility, and silver nanoparticles, which is widely used for biomedical application due to its good biocompatibility and antimicrobial properties. Material and methods. So in the preparation, both nanocomposite and parent hydrogel were prepared by using 0.2 grams of dextran in 20 ml distilled water by microwave-assisted method as a green approach. In this synthesis, in brief, in dextran solution, monomer ACM was added at room temperature. Then after thoroughly stirring, in the resultant solution, the MDA and APS was added, followed by microwave irradiation for about 15 to 20 seconds to get the hydrogel. The monomer, the MDA and APS represents N,N-methylene disaccharide which is cross-linker, and APS is ammonium peroxide disulfate. In the synthesis of nanocomposite, this hydrogel prepared was coded based on amount of ACM used, where DexGPAC1 represent for 1 ml, 2, 3, etc. In the synthesis of nanocomposite, the similar approach was used, except that silver nitrate was added before addition of monomer, crosslinker, and initiator. So in this approach, upon addition of silver nitrate in dextran solution, the solution was irradiated in microwave, and it turned to deep brown, indicating the formation of silver nanoparticle. Thereafter, ACM, MBA, and APS was added, followed by microwave irradiation to get nanocomposite hydrogel. And similar, this nanocomposite hydrogel was coded based on the amount of ACM used for 1 ml, 2 ml, and 3 ml. This is just to summarize the mechanisms. It is nothing, but as you can see, this approach and this mechanism, that the presence of initiator enabled the formation of macroradicals, where the propagation reaction took place by grafting ACM onto dextran backbone. Thereafter, the presence of MBA cross-linking two grafted chain to give three-dimensional network. Similar mechanism happens in nanocomposite hydrogel. As I mentioned earlier, here silver nanoparticles prepared before gel formation. And why this two irradiation has been performed? Because the time taken for irradiation time for nanoparticle formation and gel formation is different. So to avoid the degradation or loss of stability of gel, we irradiate in separate, because irradiation for gel formation needs lesser time than nanoparticle formation. So a list of materials prepared was taken for swelling start at pH 1.2 and 7.4 until attain equilibrium. And at each pre-described time interval, swelling ratio was calculated. As you can see in these results, there are 5 observations here. The first observation is upon increased amount of ACM, the swelling ratio decreases. The second observation is at pH 1.2, materials swell significantly than at pH 7.4. Third observation is addition of nanoparticle enhances significant swelling than parent hydrogel. And the fourth observation, the formulation with 1 ml, means formulation 1, for both hydrogen and nanocomposite, were unable to reach equilibrium because of low concentration of ACM then become very softy and difficult to handle, then we could not be able to continue recording the weight. So based on the system which attain equilibrium, the system 2 for both hydrogen and nanocomposite swelled significantly than system 3, and these systems were considered as the best system for further studies. Characterization for FTIR, the characterization of pure dextran revealed the presence of OH, CH, and CO group. I just mentioned some unique bands, not all bands, but upon the grafting of monomer in this dextran, the characteristic band at about 1600, 1400, and 1100 have been observed representing CO, CN, and COC functional groups. Similar addition of silver nanoparticle revealed by the presence of weak band at about 700 centimeter inverse. Pure drugs show some unique band at 3500, 1600, and 1500, representing OH, CO, and C double bond O. So the last two peaks are nothing but just included here to show that the incorporation of drug in these systems of hydrogel and nanocomposites show successful incorporation by appearance of some unique bands of drug. So I will show you later how the drug is loaded in this system, but not to lose this comparative peaks, I just included this in this section, in this slide. Then characterization by FESM and EDS, the hydrogel shows smooth surface with few distributed pores, but upon incorporation of nanoparticle, the surface of the material become more undulated and pores were interconnected each other. EDS confirm elemental distribution or present in the system, particularly this dextri nanocomposite hydrogel. But XRD shows amorphous nature for hydrogel, but upon incorporation of silver nanoparticle, the appearance of crystallinity peaks reveal the incorporation of silver nanoparticle. HRTM is further confirming the presence of silver nanoparticle in the material, polymer matrix. Drug loading and release efficiency. The drug is loaded to both hydrogel and its nanocomposite by swelling equilibrium method, where at room temperature, the prepared materials were immersed in seawater solution, having a concentration of 0.5 mg per ml in 1:1 distilled water ethanol for 25 hours in dark solution. So 25 hours is selected because it's near at this time is where the material reach equilibrium. And that condition is to avoid degradation of seawater. And the ethanol and water is used here because this material is not seawater, is not soluble in water. So we use ethanol to ensure that it dissolves, but to ensure that the material swell so that the drug can diffuse inside the polymer matrix, we added this water so as it can enhance the swelling and diffusion of the drug. Then using calibration curve, drug release efficiency and encapsulation efficiency were calculated, where for nanocomposite hydrogel shows higher swelling, drug loading, and encapsulation efficiency. In vitro drug release was performed in buffer solution of pH 1.2 for 4 hours and 7.4 for 24 hours. So 4 hours was selected because the drug can spend maximum 3 hours in stomach, while it can spend more than 6 hours in intestinal tract. So at this drug release start, we perform using tablet dissolution test at RPM 100. Then the amount of drug release were calculated using calibration curve at a respective pH. So the results show that higher drug release was observed at pH 1.2 than 7.4, and hydrogen nanocomposite showed higher drug release than its parent hydrogen. These results agree with the result for swelling and drug loading. Kinetics of drug release and mechanism was also performed using various models, and it is observed that the drug release kinetics for first order kinetics based on correlation coefficients, means R square value. This revealed that the drug release not only depends on the concentration of the drug, rather it also depends on the nature of the delivery system. And kinetic mechanism obeyed best fitted with Higgs square root mode, which indicates that diffusion is only drug release is controlled mainly by diffusion. While based on the coefficients, diffusion coefficients, it has been found that drug release patterns are there to non-frequent diffusion. As you can see, the value of N is above 5.5, but it is less than 1. So this reflects the non-frequent diffusion, which means that both polymer relaxation and diffusion rate are comparable in drug release. So to conclude this, dextran-based silver nanocomposite hydrogel was successfully developed and evaluated for controlled drug release, which is CUR and anti-cancer drug. The grafting, cross-linking, and incorporated nanoparticles were confirmed by FTIR, FSM, EDS, XRD, HRTM techniques. Silver nanoparticle significant enhanced the swelling, drug loading, and release efficiency of hydrogel. A higher release of CUR was observed at pH 1.2 than at 7.4. Therefore, the developed nanocomposite hydrogel appeared to be a suitable matrix for oral delivery of CUR for cancer therapy. However, this study is in progress to assess cytotoxicity, degradation, and antimicrobial activity of prepared nanocomposite hydrogel. Thank you very much for your attention.
Very nice presentation. You have done a very rigorous study.
Thank you, ma'am.
But can you tell me, while in your swelling study, you have taken 1.2 and one more pitch, I think 7.4.
Yes, yes, yes.
So what is the reason for selecting these two different pH ranges?
Yes, we have taken these two different pH ranges so to just reflect the simulated gastric condition and simulated intestinal condition, because application of this material is oral for oral delivery of CUR. So it is mainly passed through the stomach, which is acidic in nature environment, and after that it goes to the small intestine, which is an intestinal tract, which actually is basicity, slightly basicity in nature. So we just wanted to see among these two pH value, which one can significantly swell, material can swell significantly, because the drug release also depends on the swelling of the material. Once the polymer matrix relax, is where the drug can release outside. And the same way in drug loading, once the material swell, it means the drug can diffuse to the polymer matrix. So we did this just to reflect the real situation of the oral administration of the drug, which is the stomach and intestinal tract.
Okay, thank you. Thank you so much. Nice presentation, very good.
Thank you, ma'am. Can I close it?
Yes, yes, you can close it.
Okay,
You can call the next participant if we have. Next participant.
Yes, I invite Mr. Anurag to share his presentation.
This is the last one, Sushma?
Yes, ma'am, this is the last one.
Good evening, ma'am. I am Anurag Mishra. Hello.
Share your screen, Anurag.
Okay, ma'am. Is it visible?
Yes, yes.
I am Anurag Mishra, a student of PhD in. I am doing my PhD from MIT University, Gurgaon, Haryana. I am going to present characterization of antibiotics by LCMS and remediation by using nanomaterials. First of all, introduction. Antibiotics are vital pharmaceutical used to treat bacterial infections. However, their widespread use has led to environmental contamination, causing potential risk and ecosystems and human and livestock health. Evaluation of extent of the problem and use of nanomaterials, uh, nano-remediation techniques like graphene oxide can help mitigate this issue. Liquid chromatography tandem mass spectrometry is a sensitive and specific technique that can be used effectively to study environmental antibiotic contamination. High concentration of antibiotics of high contamination of antibiotics in soil and water increases the prevalence of antibiotic-resistant bacterial species. With rapid increase in population, demand of water is also increasing, necessitating improvements. Graphene oxide is a nanomaterial with a high surface area that unique physico- physicochemical properties, making it promising candidate for remediation of contaminants, including antibiotics in the environment. We have collected the sample from 3 different places. First one is Tilaknagar, Delhi, and second one is Sector 13, Sector 37, Gurugram, and Yamuna Barrage, Wazirabad, Delhi. After collection, we extracted the antibiotics from the wastewater with the help of Oasis HLB cartridge. First of all, we precondition the Oasis HLB cartridge with 6 ml of methanol, and next step is washing of cartridge with 6 ml of 10 millimolar ammonium acetate with pH 3.5, and after washing, we pass 50 ml of wastewater through cartridge, and the antibiotics present in the sample binds to the cartridge. After passing the sample, we wash the column with 5% methanol, and after washing, we elucidate the antibiotics in 2 ml of 100% methanol. After extraction, we lyophilized the antibiotics under vacuum and for studying LCMS, we reconstituted the methanol. We reconstituted the sample in 10% methanol. Synthesis of graphene oxide. Hammer's method of synthesis. Graphene flaxes and NNO3 were mixed in 50 ml of H2SO4 in 1 ml 1 liter volumetric flask kept under at ice bath. The mixture was stirred for 2 hours at this temperature, and potassium permanganate was added to suspension so carefully that temperature should maintain to less than 15 degrees centigrade. Sample was stirred at 35 degrees centigrade until it became pasty, brownish, and kept under stir for 2 hours. After 2 hours, it is diluted with slow addition of 100 ml of water. The reaction temperature was rapidly increased to 98 degrees centigrade. Color changed to brown. Further, this solution was diluted by 200 ml of water. That to terminate the reaction, 10 ml H2O2 was added, which changed the color of the solution yellow. After termination, mixture was washed with rinsing and centrifuge with HCl 10% and deionized water several times. After drying, the filtration of at room temperature under vacuum graphene oxide obtained in powder form. LCMS analysis. Graphical analysis was chromatographic analysis was performed on an equity 1 class UPLC and 0 TTD mass spectrometer. Chromatographic separation was performed on the water C18 column 2.1 mm into 50 mm 1.7 micrometer diameter. The column temperature was maintained at 30 degrees centigrade. The auto sampler temperature was set at 10 degrees centigrade. The mobile phase consisting of elements A is 0.1% formic acid in 5% methanol and B is 0.1% formic acid in 100% methanol. And the flow rate was 0.4 ml per minute using linear measurement. This is the mass analysis. Adsorption of antibiotics and graphene oxide. Graphene oxide has exhibited moderate performance in the removal of antibiotics. The graphene oxide adsorption speed and removal efficiency of antibiotics is up to 100% for some antibiotics. Antibiotics identification and quantification. We got 3 antibiotics in our our wastewater sample. First one is ofloxacin, amoxicillin, and erythromycin. And their concentration. The study found that the most widely used group of antibiotics are present in surface water of urban areas. Ofloxacin was shown to have the greatest concentration of all the examined antibiotics. Uncontrolled excessive consumption and the release of untreated wastewater into different channels may be the causes for high concentrations of antibiotics. Yeah. Thank you.
Very good topic you have chosen. Can you show me first 4 slides? Yes, you have used this graphene oxide. Extent to the problem in the use of nanoremediation like graphene oxide can mitigate this health issue. So graphene oxides, how you have prepared?
Now I don't prepare this. I work on only LCMS part. I will work further. I am a PhD scholar, so now I can't do this.
Okay. And you have said that ofloxacin is the maximum found as an antibiotic in all the areas which you have selected, right?
Yes, sir.
Okay. So, have you studied the readiness of different antibiotics on the environment, or it is more or less same for every antibiotic?
Sorry.
The harmful effects of the antibiotics. Have you studied different antibiotics?
No, ma'am.
Okay. You must incorporate such studies.
Okay, ma'am.
Okay. So thank you so much. Thank you so much. Nice presentation.
Good evening, everyone. Now we have finished all our oral presentations. Thank you so much, Dr. Achal Singhal ma'am and Dr. Sunita ma'am for taking out time from your busy schedule and chairing the session. And thank you so much all the participants for sharing your informatory presentations and your active participation. So with the permission of chair, I would now end the session.
Right. Close this.
Thank you, ma'am.
Thank you so much.